Good morning, everyone. This is the sixth and final section of Chapter 5. This is the first segment. This section essentially covers the so-called half-angle identities. And to keep things down to a dull roar, what I think I'm going to do is I'm going to derive the identities, which don't take a huge amount of time. We've set most of the stage for that. And then I've got a couple of sample problems that I'd like to work through using them. We'll see how far we get. We may have 2 or possibly 3 video segments for this. So with no further ado, I'll shift over here to the document camera and we'll start working. Okay, so this is section 5.6, page 1. What we're wanting to do is we're wanting to develop so-called half-angle identities for sine, cosine, and tangent. That's kind of our goal here. Now, the fact of the matter is that these sine and cosine, they look pretty similar. And then tangent, we're going to develop at least 2, maybe 3 versions of this one for tangent, because it does some things that are pretty slick. These 2 have radicals in them and there's really no way to remove them, but with the tangent argument we can do kind of a quick trick and we can get the radicals out of the equation. So it turns out to be pretty slick. So first off, let's start by deriving the one for sine. So the key is to work from the double angle identities. And so recall that if we had some angle, if we wanted to write the cosine of twice that angle, then this is going to be, we had 3 different choices, but the one that I'm going to focus on is the one involving sine. So we had 1 minus 2 sine squared of theta. That was the so-called second version as we derived it. Now, what we might do, this allows us to say if we know some information about the angle, then we can find some information about twice that angle. So could we reverse the process? If we knew something about twice the angle, could we find something out about the angle? And it turns out that it really is possible to do that. So what we'll do is we'll rearrange this equation and solve for sine. So doing that, we end up with 2 sine squared over theta is equal to 1 minus cosine of 2 theta. It's a little quick algebra there. And then solving this, we're going to divide by 2, and then we're going to take the square root. Now, when we take the square root of both sides, this creates that plus or minus problem that we've seen over and over again. 1 minus cosine of 2 theta over 2. So let's be clear about what aside from the fact that we have this plus or minus, we can find the exact value of sine of theta or sine of any angle if we know something about the cosine of twice that angle. So what this looks like is sort of a way to be able to take some angle and cut it in half. And in fact, that's what we're going to do by making this simple substitution. So let's say let x equal 2 theta. So theta is equal to x over 2. And rewrite this equation using x. So we have sine of the half angle is equal to plus or minus the square root of 1 minus cosine of the angle over 2. And everything's under a square root. Normally you'd simplify this, but for whatever reason, it's standard to see it this way, where everything is under this radical. It's just kind of it's bizarre, but it's also the way that you always see it. Now, let's do a really let's just go ahead and derive the one for cosine, because it works very, very similarly. But I'll just kind of box this off for now. This is the half angle identity for sine. Now, starting with the same sort of premise, except we'll use a different version of the cosine of 2 theta. Remember, there was one that had only cosine in it, and that's where we're going to start from. So we have cosine of the double angle is equal to 2 cosine squared of that angle minus 1. And again, we're going to try to isolate the cosine theta term. So we end up with, and I'll skip a couple steps in here because they are pretty rudimentary. Cosine of theta is equal to, 2 cosine squared of theta is equal to cosine of 2 theta plus, well, usually the way you see it is 1 plus cosine of 2 theta. And then we're going to divide by 2 and take the square root, which again gives us something that looks a little bit like this here. In fact, it's almost identical except for the change of the SIGN on this. So cosine of theta is equal to plus or minus the square root of 1 plus cosine of 2 theta over 2. And everything here is under a radical. Again, we'll make this same substitution where we replace 2 theta with x, and so theta becomes x over 2, and we end up with the half angle identity for cosine, which is cosine of the half angle is equal to plus or minus the square root of 1 plus cosine of the angle divided by 2. And again, the text and nobody ever makes any attempt to rationalize this denominator. It doesn't really clean up anyways. You end up with 2's everywhere and whatever else. Okay, so that's the half angle identities for sine and cosine. Let's talk about the half angle identity for tangent. And what I'm going to do is I'm going to actually use the identities we just created. So section 5.6, page 2. So if we wanted to find a formula for a tangent of x over 2, well, it makes sense that maybe rather than trying to reinvent the wheel, we just use the ratio of sine of the half angle divided by cosine of the half angle. This is just a quotient identity. And then we just substitute in what we had before. So that's going to be plus, in the numerator we have plus or minus the square root of 1 minus cosine of x over 2 over plus or minus the square root of 1 plus cosine of x over 2. Now, we're going to simplify here. Notice this is a complex fraction and also has radicals in it. Let me make one comment. If I have a plus or minus here and a plus or minus there, that reduces down to a single plus or minus. These have the same denominator, and so we can kind of get rid of them, leaving us with just 1 minus cosine of x in the numerator under a radical and 1 plus cosine of x in the denominator under a radical. So between those two terms, they're under one big giant radical. Another way to think about this is you could write this as a product and you'd see some cancellation. But the net result is that you're going to end up with an expression, tangent of x over 2 is equal to plus or minus, and this is the square root of the ratio 1 minus cosine of x over 1 plus cosine of x. Not terribly satisfying because it looks even uglier than the other ones. But this is one of those versions. Now, what I'm going to do, I think, is I'm going to derive one of the versions, one of the sort of cleaner versions for tangent of the half angle, and then I'm just going to allude to the fact that there's some manipulation you can do to get another one, and I'll just write it down rather than actually deriving it. Well, we'll see how much time we have. If it's not too big, I'll go ahead and derive it too. So first off, let's make this observation. Notice that if you were to ignore the radical for a second, just pretend like it's not there, then this term, this 1 plus cosine of x, as you may recall, is one of those things we've been talking about where it's like, well, if you see this binomial in a denominator, it makes sense to maybe multiply by what I've been calling the trigonometric conjugate. Now, the only difference here is that this is actually under a radical. So what I'm going to do is I'm going to multiply this expression on the right by the square root of 1 minus cosine of x over 1 minus cosine of x. Okay, because we're going to see some neat things pop out of this. Because for one thing, we're going to get that Pythagorean identity substitution in the bottom, which happens to be squared, and then we're going to have a perfect square in the numerator. So let's multiply this stuff out and see what we get. So we've got the square root plus or minus the square root of 1 minus cosine of x quantity squared over 1 minus cosine squared of x. Right, that's when we multiply the expression by this. So now the thing in the top, the square root will cancel with that squared term, that exponent there. And in the denominator, this becomes sine squared, which is also a perfect square. So maybe I'll do that in 2 steps. This is plus or minus the square root of 1 minus cosine of x squared over sine squared of x. And this whole term is a perfect square. And so when we simplify this radical expression, this just becomes plus or minus 1 minus cosine of x over sine of x. But we can do one better. All right, we can do one better here because we can now actually get rid of this plus or minus. And I'm going to make this sort of sidebar argument here because it has to do with the SIGN of this term. It turns out that the SIGN is right for whichever quadrant x happens to be in, at least if you're not dealing with really crazy values. But this is typically what is done is to say, okay, well, let's look at if x is in the first quadrant, what is x over 2? And if x is in the second quadrant, then where's x over 2? So I'm going to go ahead and maybe do this over to the side. So if I said if x and x over 2 if x is in Q1, then it should make sense that x over 2 is in Q1. If x is in Q2, then x over 2 is still in Q1. If x is in Q3, then x over 2 will now be in Q2. And finally, if x is in Q4, then x over 2 will still be in Q2, okay? Now remember, because the plus or minus is all based on quadrants. So let's go through them one at a time. Supposing that x is in Q1, all right? That means that this SIGN of all of these trig functions is positive. So you have 1 minus a positive number that is less than 1 over a positive number. So you have essentially a positive numerator divided by a positive denominator gives you a positive term. And then what would we do with this plus or minus? Well, tangent has to be positive in quadrant 1 as well. And so we would use the positive branch, right? We wouldn't use the negative. So that's that kind of logical argument based on quadrants. Suppose then, so that's, let me just kind of keep this running total. We would use a plus sign if this was the case, right? And if x was in quadrant 2, then cosine would be a negative value, but less than 1. So this term up top would be positive. In fact, this term up top will never be negative. It's really about the SIGN of the denominator, but let's go through it. So this will be a number greater than 1, and sine will be positive in quadrant 2. Okay, sine will be positive. So this whole ratio is positive. Now the question is, what's the quadrant of x over 2? Well, that's still quadrant 1, and so tangent should be positive. Again, we would only use the positive branch. Moving to quadrant 3, both cosine and sine are negative in quadrant 3. So this numerator, again, will be a positive quantity greater than 1, but now the denominator will be negative. So you have a positive number over a negative number. This whole term is now negative. So the question is, what is this SIGN of tangent of x over 2 in quadrant 2? Well, it's negative. So you'd have a negative term. Already, we don't need this negative sign. We would, in fact, use the positive branch. Let's just, to be thorough, let's go ahead and do the last one. So in quadrant 4, cosine is positive, sine is negative. And in quadrant 2, tangent is negative. Okay. So quadrant 4, sine, cosine, sine is negative, cosine positive. So positive cosine, but less than 1, this will still be a positive number, so positive numerator. The denominator is negative, so the whole term will be negative. And if we were to try to figure out what the SIGN of tangent of x over 2 is, well, in quadrant 2, it's negative. So you'd have a negative term. Already, we would use the positive branch. So it looks like no matter what angle we use for x, we always end up using the plus and never the minus. So we can just absolutely just get rid of that term. So the net result is that tangent of x over 2 is equal to 1 minus cosine of x over sine of x. And we don't have a plus or minus, which is kind of why this one's a little bit cleaner, a cleaner version. Okay, and I think maybe this might even be an exercise, but I'm gonna just, since I think I'm getting to a good stopping point here, I'm just gonna go ahead and write the other version and kind of leave it up to you to show that this is true. It's a very similar kind of argument. You go back up here and notice, well, you know, let's just go ahead and do it. I mean, we've got basically infinite amount of time here. So, okay, so what I'm gonna do is maybe start over from this original expression. Now, what we did here was we multiplied by this trigonometric conjugate under a radical blah, 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 basically a fancy version of 1. And we did that to rationalize the denominator, right? But notice the numerator has similar looking properties. And it makes you think, well, maybe if I do this with, instead of the radical of the ratio 1 minus cosine of x, I might be able to rationalize the numerator, which actually turns out to be a skill that you develop in Calculus 2, or sorry, Calc 1, because often for certain processes, it is better to rationalize the numerator than the denominator. You leave a bunch of radicals in the denominator, but the numerator has to be clean. And so this is not totally crazy. So we're going to start back over, and instead we're going to multiply by the term square root of 1 plus cosine of x over 1 plus cosine of x. Okay, and what we end up with there is we have tangent of x over 2 is equal to plus or minus the square root of 1 minus cosine squared of x over the quantity 1 plus cosine of x quantity squared. Again, we make the substitution for 1 minus cosine squared of x. Note that's a Pythagorean identity. We make this sine squared. And we have plus or minus the square root of sine squared of x over 1 plus cosine of x quantity squared. And notice now this whole term, this whole fraction in here is a perfect square, and so in some sense the radical unzips that, and we end up with just plus or minus sine of x over 1 plus cosine of x. And we can make exactly the same argument as we did before with all those quadrants, but what you'll be left with is that this plus or minus just simply goes away, and that the SIGN of this ratio here is always correct for any value of x. Now we could have proved that this was true by just working an identity from the second one, and it might not. I mean, it's actually relatively simple to do, but you might try. You know, without any appeal to tangent of x over 2, you might try proving that this is equal to this using some other technique. I think if I remember correctly, I think it's like a 2-step proof, because you just end up multiplying the numerator by the denominator of this one. You multiply this quantity by the ratio of 1 plus cosine of x over 1 plus cosine of x, and then you kind of work out the details. Some things start to cancel, and you're left with this. So you can take a look at that. It's not super important, but it is kind of a mental exercise. And I will, trying to think if maybe I have enough time. Well, let me do this. I'm going to do a real quick example of how to apply these identities. And the issue is that people, for whatever reason, when you put actual numbers into these, they goof them up for some reason. So let's just try this example. Let's say find exact value of, I don't know, let's say sine of 5 pi over 8. Okay, so anytime you see one of these eighths in there, that's a key to you that this is a half angle. Remember before when we were talking about sum and differences? I said, well, if it has a 12th down there, then you're going to be using a sum and difference and always pull out a quarter and whatever's left. Well, with these, if you see that 8, that's a half angle identity. Okay, so let's start by saying, okay, well, sine of 5 pi over 8 is equal to sine of 1/2 times 5 pi over 4, okay? And by the way, there's actually kind of another piece of information we need to know, which is what the quadrant of this argument is, because that's going to tell us the SIGN. So just to be clear here, 5 pi over 8 is in Q2, because that's going to tell us whether we use plus or minus. And in this case, because it's quadrant 2 and the function we're looking at is sine, we're going to take the positive branch. But let's continue here. So using this expression here, we have, in some sense, it's sine of 1/2 times x. So sine of x over 2, we just need to apply the formula. So this is going to be equal to plus or minus the square root of 1 minus cosine of that value, which is 5 pi over 4, all over 2. And of course, this argument about quadrant tells us that it's the plus sign. Okay, so now we just need to substitute what the values are for cosine of 5 pi over 4, which is something we know an exact value for, and then simplify the expression. So let's do that. We've got the positive branch of the square root of 1. Now cosine of 5 pi over 4, it may take you just a second. That's in quadrant 3, so it's got a negative sign, and it's a reference angle is 45 degrees or pi over 4. So the value will be square root of 2 over 2. Sorry, the absolute value is square root of 2 over 2, but it is negative because it's quadrant 3, and then we have this negative sign, which actually changes it back to positive. So this is going to be 1. The numerator is going to be 1 minus negative square root of 2 over 2 all over 2. And so this is kind of an ugly expression because it's not only got, it fails all kinds of rules of simplification, but it also is a complex fraction. So the first thing we're going to do is multiply through, fix this minus, distribute this negative sign, and then multiply everything by 2, the square root of 2 over the square root of 2, which is going to give us the square root of 2 plus square root of 2 all over 4. Which now, since this doesn't have any functions, we're pretty much obliged to simplify this as much as we can. And we end up with the square root of 2 plus root 2 all over 2, which is kind of a weird looking expression. And you might be thinking to yourself, going back to your algebra stuff, you're saying, well, is there something I can do to fix that? Is there some way to make that less complex? And I will tell you that there just simply is not. These are what are called nested radicals. There are some special cases that you can do some manipulation and maybe bust them up into 2 separate radicals, like square root of 7 plus square root of 2 or something like that. But often this is as simple as you can get it. And so even though that maybe is kind of agitating, I wouldn't let it worry you too much. But this simplification is required, this step here, and also all 3 of these. But that's as simple as you can get it. And I think I'm running long on time, so I will see you in the next video.